Hello everyone, welcome to Bangalore Theory Seminar. Today we have with us Kavya Ravichandran, who is a PhD student at TTIC, advised by Avrim Blum. She works in theoretical problems in data science and large-scale machine learning, focusing on low information algorithms and learning theory. Her talk today is titled Studies in Decision Making, Nearly Tight Approximation Guarantees for the Improving Multi-Bandit Problem, and Algorithmic Interventions for Escaping Pessimism Traps. Let's welcome the speaker. Uh, I'm quite excited about the talk, and so I'll hand it over to Kavya.
Thanks for the very kind introduction. I'm really excited to be here and tell you a bit about some of our work on decision making. So I'll focus on sort of two papers, one that's a follow-up to some work that came from here. And so hopefully, we can look at a little bit how the paper from here and our paper relate to each other. And then also this talk about the second paper, algorithmic interventions for escaping pessimism traps. And for that one, I'll focus more on like kind of the high level ideas, but definitely very happy to chat offline about more of the technical details. And so this is joint work with my advisor, Avram Blum, and my collaborators, Emily Diana and Alex Tolberg. Kind of at a high level, I've been recently working on this general direction about thinking about decision making as it's affected by the setting. So like what sort of structure you have in the rewards for the decisions that you're trying to make. Others, so how does kind of the world around you and the people who are making this decision before you affect you, and your personal characteristics. So, sorry, I need to point the pointer correctly. Okay, yeah, so in the setting, you have many options where the reward is improving, but at different rates, and you have to decide when to switch and when to persevere. So that's this first paper. And then when you're making a decision based on some private information that you have and other people's decisions, often history tends to kind of dominate, and you kind of look at other people's decisions and let that influence you in a very significant way. And so we're interested in finding out how to incentivize agents to follow their own private information. And the third kind of line of work is grit and tenacity uniformly good, and how does it interact with safety nets? And so people who are very hardworking kind of can persevere through a lot of hardship. But also another way to make help people out with hardship is to give them financial support when they need it. And so we're interested in sort of looking at how these things interact with each other. And so this is kind of work in progress. And I'm gonna focus on these first two things for this talk, but I'm happy to talk a little bit about our preliminary results and models offline for this third direction. Is that my mic? Am I good? Okay, cool. There we go. Okay, so I'll start by talking about this paper, which is joint work with my advisor, Avram. So here the motivation is maybe you have a bunch of different locations where you could drill a well and look for oil, and you want to sort of effectively search over these and kind of get to the oil as soon as possible. Or maybe you're training a whole bunch of different learning algorithms, and they have these different training accuracy profiles. And you want to figure out how to invest your resources such that you get to the highest or the best outcome with the least resources expended. And something that I think is probably familiar to a lot of us here, and which was kind of my motivation for working on this problem initially, is this question of which research direction has the best payoff. And so, we work on projects and we think about different areas, and the different ones have different payoffs, and they take different amounts of investment to get good at. And so is there a systematic way in which we can kind of choose between which projects to spend our time on? So don't take any career advice from my talk. It's just a math talk. But yeah. So okay, so the problem instance is this. You have bandit arms, you have K bandit arms. And you each one you can get some reward after pulling it for some number of times. And this is increasing. And the interaction is that you pull the arm and you receive a reward that is a function of how many times you've pulled the arm. So importantly, it's not a function of the total amount of time you've been playing the game or anything like that. It's a function of how many times that particular arm has been pulled. And so our goal is to maximize the total reward. In the paper, we also talk about how you can sort of adapt essentially the same algorithm for maximizing the maximum reward that you ever achieve, because sometimes you care about that instead. And we measure this by competitive ratio. So this is, I'll write this as opt over alg. It's the optimal reward divided by the expected reward of the algorithm. And the expectation is over randomness in the algorithm. So we're going to be looking at randomized algorithms for this problem. And past work from a group here at IISc has shown O of k upper and lower bounds for deterministic algorithms in this problem. And so as I talk about our lower bound and upper bound constructions, I will try to also compare a little bit to this paper to tell you kind of what's similar and what's different. Are there any questions in the setup or the formalism for the problem or the notation before I move on? Okay, cool. Okay, so we're going to make an assumption on the reward functions, and that's that they follow this diminishing returns property. So this is kind of concavity, and basically it says that the difference between two consecutive pulls of the arm decreases as you keep going. So some examples of functions. This is not a diminishing returns function. This is also not a diminishing returns function. But this is a diminishing returns function, and so is this. And so this is an assumption that we make because you can kind of have very bad things happen very quickly if you don't have some sort of structural assumption like this. But it is, maybe a pretty strong assumption. We can think about whether or not it holds in practice. And so, I think different applications have sort of different kinds of, like some of them, maybe this assumption holds better than others. But yeah.
So the previous one was with this assumption?
Yes, yeah. So I think the popular all paper that I mentioned also makes this assumption. I think the very first paper on this, which is this Hoda Hedari's paper, also makes this assumption. Yeah. Thanks for the good question. So I'll walk through the lower bound construction that we have, and then I'll tell you about the algorithm. And this algorithm will work extremely well if we have an assumption in place, which I'll also tell you about. But of course, we want to minimize the number of assumptions we make. And so I'll also tell you how to relax that assumption. To be clear, this is a different assumption than this. All of the work relies on the concavity assumption. The upper bound will rely on a stronger assumption about what the algorithm or the agent has knowledge of, which will then relax. So just to give you a preview, there we go. The lower bound is going to be omega square root k. Upper bound, in the presence of the strong assumption, is going to also be square root k. And then once we relax it, we're only going to lose this log k multiplicative factor. Hence the nearly tight approximation guarantees. So this is kind of the instance at the core of our lower bound construction. It's very similar to the instance from Bakula et al. But one big difference is that we move the kind of inflection point to t over square root k, whereas in their work it was t over k. And kind of intuitively, the idea behind this is that if you are in this region behind t over square root k, you can't tell the difference between the good arm and all the bad arms. And so, you know, you're going to keep playing it until you can actually distinguish them. But once you've played it that long, you have, you might have to go back and restart, in which case you only have a small probability of actually finding the good arm. So
I said like when in complete ratio is set, we'll also be looking at randomized algorithms. So this lower bound that you have is for randomized algorithms.
Yes. Yeah, great question. The lower bounds for randomized algorithms, and the way we're going to show this is using Yao's min-max principle. And so what we're actually going to do is construct a randomized family of instances and show a lower bound on that for a deterministic algorithm. But then you can kind of switch the randomization and get it for randomized algorithms.
So my question was,
Yeah.
Okay, so this root K lower bound is for randomized. Previous one was it for randomized or deterministic?
It was for deterministic algorithms. Yeah. So first we can lower bound the optimal reward, which is just if I play the blue arm the whole time, and that's at least t over 2. And then we need to upper bound the reward of an algorithm that plays this instance. So in order to do that, we're going to define a related but slightly different game and then translate what reward we get in that game to what happens in this actual game that we're playing. So this is what that game looks like. The universe sets all k of the arms to have the orange reward function. A deterministic algorithm runs for t steps on that instance. And then the universe chooses one arm, I star, uniformly at random, and changes its reward function to f star, the blue function that went all the way up. And then we check if the deterministic algorithm played that arm I star for at least t over square root k steps. And if it did, then we give it all opt of the reward. But if it didn't, it just keeps what reward it gained originally. So we can observe that the algorithm wouldn't change its behavior based on I star if it only played it for fewer than t over square root k steps. And because of that, the game that we've defined on this slide is actually more generous than the original game, right? So if the algorithm has played I star for more than t over square root k steps, we're saying we're not even going to count how many steps it played I star for. We're actually just going to give it all of opt. And we know that the algorithm could have played at most square root k arms for longer than t over square root k, for t over square root k or longer. And so we can use this to say that with probability square root k over k, alg gets opt. Probability at most square root k over k, alg gets at most opt. Plus, with probability at most 1, alg gets just playing one orange arm for the whole duration. And so we can upper bound this in terms of opt and opt over square root k times a constant. So as I said, we apply Yao's principle to take this randomized family of instances and convert and deterministic algorithm and convert that to a lower bound for randomized algorithms. And we get a lower bound of order square root k. Are there any questions on the lower bound? Yeah.
It would be then that like in this case, I think you don't know T. Or I think you know T.
I think we're assuming we know T. And the construction as written is like scaled by that T, but the multiplicative square root k applies even if you don't scale it that way.
we don't know is it still root kill output or?
That's a good question. Let me think 1 second. Yeah, that sounds good. I'm inclined to say yes because I don't think that. So I don't think this we like rely on the deterministic algorithm like knowing the time horizon. But we do rely on the fact that it's like bounded. But yeah, maybe we could discuss this offline. Yeah. So now I'll talk a bit about the algorithm and the upper bound. And so we're going to start with this assumption, which is quite strong, that we know the maximum value of the best arm, so f star of t. And our strategy is going to be super simple. We choose a random arm and we keep playing it until we can no longer hope to get f star of t reward eventually. And so what this looks like is we start with this blue arm. We'll pull it and we project and see if it reaches this red line, which is our not what we know of as f star of t, capital T. And we keep pulling the arm until the line can no longer intersect the value of f star of t. And so this kind of has a similar flavor of optimism to the upper bound in the previous work, which also sort of looks at, kind of projects forward what that arm could hope to do, or how good that arm could hope to be, and tries to use that in deciding how to switch between arms. Yeah.
Adding like origin with the present value.
Yeah.
How do we get the gradient at that point?
Yeah, you can. I think so 2 things. One, it doesn't really change the analysis because of the diminishing returns property. Like it only helps you to do what you're describing. And 2, this means that we can use similar triangles to compute the area. So it just made it simpler analysis wise. But I think, yeah, like if you're, implementing this in practice, probably the more sensible thing to do would be to use like the last 2 consecutive points to project. Mhm.
Capital T.
Yes, yeah.
So here also we are assuming T.
Yes. So yeah, so good question. In this part, we're assuming, and in the talk, we're assuming that we know capital T. But in the paper, we show that you don't actually need that assumption because you can use a doubling trick. So you can just guess some T prime and then kind of run it for that long, and then if the world hasn't ended yet, you can just continue playing for twice as long. And this again only loses you constant factors. Yeah. Okay, so in order to analyze this, one thing that we really need to understand is how much reward do you get when you play an arm for TI steps? And so, as I said, we can kind of exploit similar triangles to do this. So we're interested in this orange region because this is a lower bound for the amount of reward that you get from playing the blue arm. And so we know what the side lengths are. This is TI -1, with this -1 coming from the fact that you need the last pull to know that you're no longer going to succeed on that arm. And then the base of the big triangle is T, and the height of the big triangle is M. And so we get the height of the small triangle and use that to compute the area of this triangle, to lower bound the area of the reward that you've achieved so far. And we can actually just rewrite this in terms of the optimal reward as well. And so this is kind of a key piece of our analysis that we will then use in the next step. So I want to highlight for this next step recursive structure in the algorithm. And so inside we have this repeat block, and that block essentially says that you pick a new arm and then you pull it until this condition is no longer met and keep getting the reward from the arm. And so essentially you can think of this as playing the exact same game again, but with one fewer arm and TI fewer steps. And so so we can use that in order to analyze the algorithm. We can define this recurrence V of T prime K prime as something like the expected reward when playing the game with T prime time steps and K prime arms. And there are some like subtleties here that we kind of, that felt kind of technical, but sort of were necessary in order to get this analysis to work out. And I didn't include them in the talk for like kind of clarity of message, but I'm happy to talk about them, about those subtleties offline. But yeah, so we use this recurrence V of T prime K prime. So in order to, so we can't actually write we don't actually like say the recurrence is equal to this, we just lower bound it, which suffices for our purposes. And so with probability 1 over K prime, you get the optimal arm, you get the optimal reward from that arm. And then with probability 1 minus 1 over K prime, you get whatever reward that you get from playing the arm that you played, plus the recurrence for T prime minus T and K prime minus 1. And so this first term is the reward from an arm that you play for T plus 1 steps. That follows the previous slide, kind of this orange triangle, what we computed as the area of the orange triangle. The second term is the expected reward for the rest of the game. But importantly, we don't know which arm we're going to pick, and which arm we pick determines how many steps we play that arm for. But we can safely take the worst case over arms. And so you just take kind of the worst case T. So in fact, you can take the worst case over arms and also actually just take the worst case over T, which is what we do. And we solve this recurrence using induction to get that. This is lower bounded by octave T prime divided by, O of squared K prime. So with a little bit more subtlety and some analysis, we can get then that the competitive ratio is upper bounded by order of square root K when we know what this best arm's final value F star of T is. Are there questions on the upper bound or that analysis? It's just a constant. I screenshotted this from the paper, so it's in the paper you can think of it as 2. Like it's just so that we have an interval in which the this like maximum value lies. That's or actually, sorry, to be more precise, it's the constant that links the maximum value to the optimal reward. So essentially, because of this diminishing returns property, you have that the total amount of reward under that arm is at least the triangle under it, which is like m times t divided by 2, and it's at most m times t. And so like if m is actually f star of t, then you just need a factor of 1, so c is actually 1. But if you have like some uncertainty in your estimate of f star of t, which is what we'll get to in the next section, then that constant is something a little bit. Okay. Oh yeah.
Constant. How big is it?
So okay, so yeah, so C2, if you know, like for this section, it's just 1. Oh, yeah.
Order constant. Because I remember in our paper, some compare that though we give tight algorithm for deterministic algorithm, the constant fell like 60 or something. I just wanted to check, like, is it a small constant?
I'm glad to hear you got that review too, because yeah, it's I think it's like in the hundreds, like 128 or something like this. It's a couple of factors of 2. Yeah, so we didn't work very hard to get rid of those constants. And you know what? It's an interesting question. Like, I guess from my perspective, like, it's already interesting to think about the order of the competitive ratio. But yeah, people have been very interested in this issue of the constants. So I'm, yeah, it would be maybe nice to get like tighter constants for the upper and lower bounds, but our work doesn't do that. Yeah. Yeah. The constants are in the paper. We have the theorem statements just have the constants. So So in reality, like we don't know what the F star of capital T is. We don't know, what's the best possible paper that you could ever write or, whatever. So we're studying a bandits problem. What do? We explore. And so we're going to estimate this parameter by just exploring for half of the time and then exploiting for the other half of the time. And the exploitation phase just uses the algorithm in the previous part. And I'll talk now about how to do this exploration and kind of figure out a good guess for the F star of capital T. Okay. Okay, so how do we explore? We just pull each arm T over 2K times, and we kind of get a sense for what the initial profile of each arm looks like. And then we extrapolate upper and lower bounds for where each arm will end up. And we kind of rely on this, again, diminishing returns property in order to do this. And so we know that it's not decreasing, and so the lower bound is always just flat. And then we know that we have diminishing returns, and so you can just take the current slope and project upward to get the upper bound. And now that we have that for each individual arm, we can combine that to get an interval u comma L. This L should actually be a little bit higher up. It's not actually the smallest one. It's like something a little bit different from that. But the key point is that the size of this interval in terms of the ratio between u and L is order k. So once we have that interval, we divide it into subintervals of doubling length, and we choose one of them at random, uniformly at random. So with probability 1 over O of log k. And so now, yes.
Where are you starting with? Like that.
Capital
That
T.
yellow line, like where are you starting it?
At capital T. Yeah. So like I said, for the talk, I'm assuming that we know capital T, but we show in the paper that you kind of do it with like the doubling trick if you don't.
Is it obvious? Why?
It's like not. I wouldn't say it's obvious because I spent a little bit of time trying to prove it, but it's like clear from the properties. Like it comes from this diminishing returns property. Basically so I think it's like relatively clear that the size of the interval for one of these arms is order k. Again, because of like similar triangles. But the fact that you can't just pick the highest one because the maximum value for the best arm could lie below that, but it can't lie below that by more than a factor of 2, which we also show in the paper. And so what you actually get is like more precisely like this. Like I guess I tried to make this L not aligned with this, but it's like half of this, and so I think I had to have it there. So yeah, does that make sense? Okay. Yeah. So now we choose this. We choose an endpoint with probability 1 over O of log k, and we choose an endpoint uniformly at random, and then with probability 1 over O of log k, it's within a factor of 2 of the F star of capital T. So if you have a good guess, you get the same reward that we discussed in the previous part of the talk. And so then the expected reward competitive ratio is at most O of square root k log k. And so this is kind of the like outcome once we make that make that relaxation of the assumption. And like I said in the paper, we also talk about, not knowing T, the time horizon. And we also talk about kind of a noise model where you don't exactly see the function value, but you see it like within some interval. And we show that, you can also solve the problem in those cases. Okay, so to draw some conclusions, and like I said, don't take career advice from my talk. I would conclude that you should try everything for a bit, and then make a good guess about what's achievable, and then from there only work on things that will get you there. But really, this is a theory talk, and this is the real conclusion, which is that the competitive ratio for this problem is between O squared k and O squared k log k. Yeah, so that kind of concludes the first part of the talk, or the first paper I wanted to talk about. Do you guys have questions, things to talk about that? In which case I can talk a bit about this second paper called Adaptive Algorithmic Interventions for Escaping Pessimism Traps in Dynamic Sequential Decisions. After it grabs. Okay. This is joint work with, again, my advisor, Avram Blum, and then also with Emily Diana, who was research faculty at TTIC and is now a professor at Carnegie Mellon, and Alex Tolbert, who is a faculty member at Emory University. So this problem is kind of motivated by this, or a motivation is this New Yorker cartoon, where this last judge is saying, well, heck, if all of you smart cookies agree, who am I to dissent? And it sort of speaks to this point that when a bunch of people are expressing their opinions, even if your opinion is a little bit different from the group, you're kind of incentivized to not deviate from the group's opinion. And the kind of motivation that we care a little bit more about and sort of inspired this line of work is kind of the way people have defined pessimism traps in the philosophy literature. So this philosopher, Jennifer Morton, has talked about how a pessimism trap captures how negative beliefs about one's likelihood of success can play a role in agents pursuing less risky, modest ends instead of ambitious ones, thereby further entrenching the negative evidence that the agent herself and other agents in a similar position face. Poverty, prejudice, and discrimination play a role in providing agents with the sort of evidence that would make it rational for them to arrive at the pessimistic beliefs that play a role in thwarting their ambition. And so it's important that these are rational. So you can imagine a situation where in a community, in a town or a village, everyone sees people before them kind of working stable jobs and maybe like working in certain trades. And so when a teenager is thinking, should I go to college, or should I take over, start working at my family business, they don't have a reason to believe that going to college is going to be a good decision for them. And on the one hand, this is because they have very stable and reliable alternative options. But on the other hand, it still keeps this individual, but this community more broadly, in these sorts of like pessimistic worldviews. And so what we're interested in is understanding whether a central agency, say the government, can intervene in such a way that they sustainably shift the community toward optimism. So do you have any questions about what a pessimism trap is, or do you sort of have a sense for how that works? Okay. So in the rest of this section, I'll introduce the formal model that we use to look at pessimism traps, sort of with mathematical formalism, since a lot of the prior work on pessimism traps has been either from philosophy or education. And then I'll focus on a case where there's a single community and we're interested in a intervention from the government that tries to shift this community away from pessimism traps. And then I'll extend this to the multi-community setting where you have k-parallel communities, and they each kind of have their own best action. And we show that a government can still intervene in such a way that everybody can move toward what's good for that community. Okay, so let's start by defining this information cascade model. This model takes, it looks at sequential decision making in agents, and each agent has a private signal SI that only they know. And then they take some action HI, which contributes to the history of decisions made by agents. And this happens sequentially. So each agent has access to the history of the agents before them and their private signal, but they don't have access to anyone else's private signal. So for instance, okay, sorry, before I get there. So these agents could either be living in world A, where action A is the correct action, the reward for that action is 1, and action B is the incorrect action and the reward is 0. And in this case, their signal is going to be A with probability P bigger than a half, and B with probability 1 minus P less than a half. Or they could be in world B, where sort of the opposite is true. So in world B, B is the correct action, the reward for B is 1, the reward for A is 0, and then the signal is still aligned with the correct action in that world, with probability P bigger than a half, but in this case, that's B, that's action B. And for this section, we assume that the actual state of the world is that we're in world A, but this isn't known to the agent, and it is known to the government. Of course, in the last section, when I talk about the multi-community setting, I will relax this assumption. Are there any questions on the information cascade model? Oh, I didn't finish defining it, apparently. So agents choose between action A and action B, and they do so by trying to maximize expected reward. And they, in order to do this, they have to compute the posterior for the probability that they're in world A, given their signal SI and the history of the agents, the actions of the agents before them, HI minus 1. And they have a uniform prior between the worlds. So one reason we kind of like this is because if you're a Bayesian, which some people are, this is a good way to formalize rationality. And so it was important in Morton's work on pessimism traps in philosophy that pessimism traps are completely rational. So they're not, it's not some sort of like irrational behavior from an agent. It's like something very consistent and rational. And so this is a kind of nice framework to start thinking about that, we think. Yeah.
So
Yeah.
HI minus 1. So does it mean that the agents are like making decisions sequentially?
Yes. Yes, exactly. Yeah. Yeah.
Signal is like the opinion of that person, but HI minus is the opinions of the other person, other people that they have put out.
Yeah. It's the collection of all the opinions so far. Yeah. So I think I should have clarified this a little bit, but I think I was using lowercase h for an individual's action, and then uppercase H kind of is the set of all of the history of actions. Yeah. Yeah, so I'll just work through a quick example. The first agent comes along, has signal B. They don't have any other information, so they're going to act. Their posterior calculation is basically just what's the probability of their signal being. Okay, so what's the probability of being in world A given their signals B? They do the posterior calculation, and they just choose B. They don't have any other information to go off of, and therefore they just act. Now the second agent comes along, and they have to do a slightly more involved posterior calculation. They also have a signal B. And so the probability that they're in world A, given that the previous person's signal was B and so the previous person's action was B, but the action was the signal, and their signal is B, is pretty low. And so they also take action B. And now if a third agent comes along and their signal is A, they do a posterior calculation to say, okay, what's the probability that we're in world A, given the last two people took action B and my signal is A. But because the last two people took action B, there seems to be good reason that, multiple people think B is a good idea. And so their posterior is actually already much lower than a half, and they're going to override their signal and take action B. And so this is kind of a nice example of, or you can kind of already see that and these information cascades develop very quickly. So it doesn't take a lot of people acting, taking a certain choice in order for it to just like propagate throughout the system. And separate from our work, people have used information cascades to study things like fashion, where, the first person wears something because they think it looks nice, and then the second person, maybe also thinks it looks nice, and they also saw the other person wearing it. But now that two people have worn it, like that's it. That's the coolest outfit ever. And so it's kind of an interesting way to think about these sort of polarization dynamics. Okay, so the interventions we're going to look at are subsidies. For a subsidy, sort of formally, what we're going to look at is a government, symbolized by this building, giving money to the agent for taking an action that the government is choosing to subsidize. And so two kind of important things here are, one, the agents aren't going to trust the government. So just because the government is subsidizing an action doesn't mean that the agent thinks that that doesn't automatically mean that it's the right action. And the second thing is that we're going to subsidize the action regardless of the world. So if you're in world A and you take action A, you get the subsidy. But even if you're in world B and you take action A, you get the subsidy. So you're subsidizing the action. So let's look at a naive subsidy. So naive subsidy is to just give the agent a lot of money for doing the action that you want them to do. And so at the top here, I have the information cascade that we worked through earlier. But now suppose the government incentivizes action A by giving like a large amount of money to an agent that's about to take action A. And for that agent, the subsidy completely made action A worth it. They're like, cool, I'm going to do this. I'm happy. But if the government doesn't give a subsidy to a subsequent agent, that subsequent agent is going to be a little bit cynical about this and say, okay, I think the previous agent only took action A because of the subsidy. So I'm going to ignore that, and I'm going to go ahead and do whatever I think is right, which is act according to my posterior. And they're going to be stuck in the pessimism trap again. So what is our goal for the subsidy? It's that people should, there should be a bit more variation in people's behavior. And in particular, that variation should come from people's signals. And so our goal is really to encourage people to act in a way that reveals their signal. And the core idea is that we're going to incentivize action A just enough that an agent is going to do it if it's already aligned with their signal. So formally, if we have a subsidy of size R sub t, and the reward for the good action in the world is capital R, then what we want is that the expected reward of taking action A when your signal is A should outweigh the expected reward of taking action B when your signal is A. So this is natural. You want the subsidy to incentivize action A over taking action B when your signal is A. But the flip side of that is that we actually also want the expected reward of taking action A when your signal is B to be less than the expected reward of taking action B when your signal is B. So again, this is sort of formalizing this idea that we want people to act according to their signal. But what we immediately see is that there's both a lower bound and an upper bound on the subsidy value. So there's this sort of right range that the subsidy value has to lie in order for people to start revealing their signal. Yeah.
Are you deciding subsidy based on the history, or you just decided at the beginning itself?
Good question. We're doing it based on the history. For this section. Also, I realize I'm like running a little bit low on time, so about 5 more minutes. But okay. 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 I didn't know if I should pause for like end early for questions or. Okay. All right. I'll take 10 or 15 minutes. Then I might actually be able to get through everything else I have. Okay. So so we can compute this out, and then yeah, you can see that it depends on the history through this term. I'm sorry, I didn't define all the notation because I really wanted to focus on the ideas here. But this term is basically the number of A actions from subsidized people, and this term is the number of B actions from subsidized people. And so size of A minus size of B is like the term that depends on the history. So let's see. Yeah, okay. So
subsidy is something government decides.
Yes.
Subsidy on.
Yes.
But here you are like getting a formula for something.
Yes. And I'm gonna print this out and give it to the government. So this is for the government. Yeah. Yes. Yeah. I mainly put this on the slide to be like, yes, there is a closed form solution to it. It is something we can compute. Of course, like, we can talk more about it offline, or you can take a look at the paper for all the computation steps to get there. Yes, it is. So assuming this subsidy is in place, it is a decreasing function over time, yes. And so in fact, the way we can see that is by kind of analyzing what's going on here. And so recall that our goal was to incentivize kind of people acting according to their signal. But what is their signal but a Bernoulli random variable with bias p bigger than 1/2? And so we can construct a random walk to analyze this cascade, and we can ask questions like, what is the expected amount of time we need this subsidy to be in place in order for the community to be convinced that they're in world A versus world B. And so we can apply our plethora of random walk tools to get insights about how this works. So this is kind of the first big insight in the paper, which is that if you have a really small subsidy, you're stuck in pessimism, a small or non-existent subsidy. And if you have a really large subsidy, you kind of end up in this more like cynical setting, right? Where people are like, oh, that person only did it because they got subsidized too. I'm not getting subsidized too. Why would I do it? But there's this kind of middle range where you're actually making progress, and you're actually kind of incentivizing people to do the good action, but you're also making sure that it remains rational for subsequent people to do that action. So this kind of non-monotonicity, I think, it was a little bit surprising. And so now, okay, obviously the world has many groups of people, and not all those groups of people have kind of the same right choice. And so we're going to extend this to having K groups, and again, K sequences of individuals. And now each of them has a different correct choice, or they're each kind of inhabiting a different world in our original language. And so agents see the actions of previous agents in their group, but otherwise they behave as before. So they don't see, like, an agent in group 1 won't see what agent in group 3 did, but otherwise they're behaving as before. The government provides the subsidy, doesn't know group membership. So when an agent comes up to them, they don't know what group they're a part of. And so this is sort of, we think of this kind of like a fairness constraint. Like the government isn't, saying, okay, you're from this group and therefore I'm going to like provide you this subsidy, or like tell you to do this action. And in fact, the government doesn't even know which choice is correct for each group. And so that you can think of that either as like the government doesn't have that information, or you can also think of it as like, the government isn't allowed to like take a stance that like this is the right thing for this group. Okay. So the idea here is that Yeah, the idea that we're going to use to solve this is essentially just we know that there is a progress region for each of these groups based on our insight in the previous part. And so now all we're going to do is we're going to have a distribution over subsidies and ensure that there's a positive probability associated with each subsidy that's in the progress region. And so what that looks like is you have a government who only knows the signal strength, and you have an agent who has a signal. And the government is going to draw the subsidy that they're going to give this agent from some distribution. If that subsidy is in the progress region or in the signal revealing region, the agent will reveal their signal. And we can construct a random walk like I talked about before. And there's a step that's taken on that random walk. And we've made progress. On the other hand, if the subsidy value is too small, then the agent is going to act according to maybe according to their history, and they're going to pick an action that's not aligned with their signal, and we're not going to take a step on the random walk, and we're going to be in the pessimistic setting. And if the subsidy value is too large that was drawn from this distribution, then the agent is just going to act in accordance with the subsidy. And so again, we're not taking a step on this random walk. We're in the cynical setting. But importantly, like what the kind of invariant that makes all this analysis possible is that when we take a step on the random walk if and only if an agent's signal is revealed. And so given that we're using this kind of core idea, we've essentially turned the analysis for a group of cascades into a slowed down random walk. And slowed down by what? It's slowed down by the probability that an agent is from a given group. And so as long as you see each group with some minimum probability, that's kind of the factor that slows down your random walk. And then it's also slowed down by this like positive probability that the subsidy is in the progress region. So as long as for each group and for each like kind of location that they might be at in the random walk, there is a value associated with it that we can calculate based on the single community analysis that tells you like what to subsidize them in order to get them to move in the correct direction. And so provided that value has some minimum probability associated with it in our distribution that we construct, we can just slow down our random walk by that probability. So again, because it's a random walk, we apply our plethora of tools, and we can say what's the expected time it takes to get into the correct cascade for one group, for many groups, for all groups, and also we can do with high probability guarantees. And so insight 2 for this piece of work is that the sort of randomness in the subsidy encourages people to figure out and follow what is right for them. And also it's without the sort of like governmental heavy-handedness of saying like, okay, this is going to be the right action for this group. So that's it for this second paper. And then I'll just summarize whatever I talked about today. So if you have any questions about the second paper, I'm happy to take them now.
The agents follow some random order of arrival. So right now, this sequence can be adversarial. But if it is random order, does it help or it does not help?
So, okay, actually, we define the sequence to be random order. I think maybe I wasn't clear about that here, but in the paper, we okay, maybe it's actually fine for them to be kind of semi-random in the sense that as long as an agent is arriving with probability at least this, like how you pick that probability is not important, and then that probability will just show up in the term, in the like amount of time it takes to converge term.
Anyway, the example you showed even for 3 or 4 people, the progress quite quickly.
Yeah.
So random order will not get that.
Right. So also the other thing is that so okay, so I think it is. Yeah. So I guess two comments are like, one, I think so in the paper we do explicitly define it as random order. And so it's kind of important that people's signals are random and people's arrival is random. But the second thing I was going to say about that is that we kind of have to push out. So in the single community case, like the stopping points for this random walk are like plus and minus 2, because like we saw, like if you have two people that take a certain action, you kind of already start this cascade. But for the multiple group case, because you have this probability that there's a non-trivial chance that like you'll hit +2 before you hit -2, even if -2 is like your stopping point. Like even if like B is the correct action for you, you might actually hit an A cascade, just because coin flips are coin flips. Because of that, we actually have to push out the stopping points much further, and then we analyze like what is the probability that you hit like plus L, where L is the stopping point before minus L, and then use that to say that like with high probability, all communities will be at their respective optimal stopping point before any of them kind of is at the opposite one. Yeah. I can be way more precise about that offline or in the paper. Yeah. Another question? Okay. Okay, I'll just summarize quickly then. So as I said, I'm looking at decision making as affected by the setting, others, and personal characteristics. And so the kind of conclusions we drew from how is your decision making affected by the kinds of structure you have in rewards. Collect information, make an educated guess about best possible outcomes, and stop working on things that won't get you there. Just focus on the things that will, help you achieve the best possible outcome. We saw that subsidies could have non-monotone effects, which kind of goes against, at least what is to me like kind of conventional wisdom, that you give people more of a subsidy to do the thing that you want them to do, and they'll do it, and it's great. And then randomness allows people to sort of figure out what's right for them in this setting where you have different groups with different optimal actions. And I didn't talk about this last one. Happy to chat a bit about it offline, but it's still preliminary results, and hopefully we'll have that kind of written up and online in a couple of weeks to months. So, yeah. Thank you guys for listening. Here are the papers and my email. And I really appreciate your attention and wonderful questions. I'm happy to talk more.